Today, we are truly fortunate to have Dr. Selvaraju with us to share his wealth of knowledge and experience. Let us all join hands in welcoming him to this session. Over to you, sir.
Okay, thank you. Thank you so much for the introduction. Let me, just for the people who actually joined in, I actually shared my PowerPoint in the chat, and you feel free to use that PowerPoint. So let me share my screen. Cool. All right. So let me begin. So this is the session plan in terms of what we want to cover in the next 90 minutes. So before I jump into the application of AI and ML and smart grid, I just want to spend 15 minutes in terms of introducing you to something called data. And then that lays a foundation stone for AI and ML. Then we'll spend like 10 to 15 minutes on that. Then we'll jump into the application of AI in smart grid. So let me kick off with the first question. So I don't know how many people recognize this device that you see on the PowerPoint. Just type on the screen, what's the storage capacity of this device? Just put it on your in the chat window, please. So how many of you can actually say exactly the storage capacity of this device? Okay, somebody said in KB. Yeah, it's in kilobytes. Okay. Anyone giving the exact numbers? Okay, interesting. All right. So this device is called a floppy disk, and the exact capacity of this floppy disk is 1.44 megabytes. Okay, that's the 3.4-inch floppy disk capacity. So just to give you a perspective, if you take a picture in your smartphone, it won't even fit in this device. Okay. So the picture you take is usually about 5 megabytes or something, and then this device is 1.44 megabytes. Cool, thank you. So the reason I actually mentioned is, look how far we actually grown. In 1990s, the internet speed is very slow, and then even 1.44 megabytes is too much of a storage capacity during the time. But fast forward, we live in 2024, where we are producing more than 10 zettabyte or 1 exabyte of information every single day. Okay, so that's the explosion of data in the last 20 years. So let's look at what's actually driving this. Okay, so the main drivers for this data explosion is the compute power. So if you remember in those days when you buy a computer, usually it's powered by Intel chips and they have Pentium processor in it. And the first computer I ever bought is for close to 58,000 rupees, and it has a Pentium 4 processor in it, and it works at an amazing speed of 700 megahertz. Okay, let me stress that it's 700 megahertz. Your smartphone runs on more than 1 gigahertz speed at this point in time. Okay, so I'm talking about 15 years ago. So if you look at the compute power, we actually done an exponential growth. The Moore's law still holds, and so that's what it's happening. And then the internet speed. And I'm pretty sure if you remember those early days of internet, we have something called the dial-up modem. And then when you click on your computer, it makes some funny noise. okay, to connect over internet. And then it usually connects at the amazing speed of close to, if you're very lucky, if you get about 32 kilobits per second. But in those days, it's very fast. Okay. And these days, you throw away a phone where if it doesn't buffer the YouTube within few seconds. Okay. So you're talking about at least 1 megabits per second in the broadband. So the internet speed actually exploded. And the third thing that's fueling this data explosion is the smartphone. When Nokia was there, it's more about connecting people, but these days it's about WhatsApp, Instagram, and you think about other multimedia kind of an application where you share rich kind of data. Okay, and that's exactly what's driving this data growth. Okay, again, I showed you the behavioral trends. Again, if you look at the other drivers, the storage got actually reduced. Okay, I was in a conference recently and they're actually giving out 32 gigabytes of flash drive for free. And there was no takers, by the way. The reason is if you use Google Cloud or Photos in the cloud, they've given you virtually 15 gigabytes for free. Okay, so that's the uh, phenomenon that we're actually seeing. And the bandwidth cost actually reduced a lot. When I bought my first internet, I paid a huge, for a 32 kilobits connection, I paid about 1,000 rupees a month. And these days I get 40 megabits per second connection for 500 bucks. Okay, so the bandwidth got actually reduced, and even the components, the electrical and electronic components, actually reduced. So that's what's another driver in terms of fueling this. All right, so again, you're going to go to this chat window. Okay, great. I've actually given you. We are producing a lot of data in the last 20 years combined. So what do we do with this massive data? Put your answer in the chat window. I just want to understand from your perspective, very generic perspective, what do we do with this massive amount of data? Just put your couple of thoughts in the chat window. Given the new Gen Z generation and then the millennials combined with the Gen Alpha generation, they're very focused on sharing a lot of information, sharing a lot of data. Um, so we are producing a lot of this data. I already told you that the cost is zero, literally zero in terms of storing that. So what do we do with this massive amount of data? Why collect it? Just a matter of storing it. Okay, let me move on. So basically for companies, it's all about money making. It's very simple. So they collect all the data from you so they can offer you new products and services. Very simple. They shift their business model over a period of time. They offer rich value added services and then they offer new products and services. For example, the internet company I am with, they actually offering me a security camera if I pay 100 rupees a month. Okay. So again, it's a new kind of services, and they introduce new kind of products into the market as well. So that's what they do. But underpinning everything is all about dollars. Okay, great. I talked about companies. What about consumers? So the consumers, they get value. So if you look at these days, the data explosion actually helping us to save time. When you order Uber, you exactly know how long it comes. It's for convenience as well. It's given you a lot of luxury and actually improved the quality of life for a lot of consumers. And more importantly, it actually get us connected. Okay. So that's the value we offer for giving our data. So given the data discipline, if you think that there isn't any kind of discipline that's not disrupted, guess what? The electrical engineering discipline is apt for disruption. And I'll give you some examples of how. And you've probably seen this concept called smart homes, which was very popularized or very theoretical maybe 10, 15 years ago. And these days, when you go to any home, they are pretty smart. Okay. And everyone has this app. So they monitor temperature, wind speed, they control the window movements. In fact, some of them are very automatic and they also have solar panels on the top. And then that's also giving you a lot of energy savings, and the whole house is being optimized for all these things. and this is all possible because of data that we currently have. Okay, and as home used to be a very metal heavy kind of a place to be. Okay, it's all made of solids, correct? You have bricks, you have cement, you have pipes, you have valves, you have ceramics and stuff like that. You have tiles, but these days it's already been the electronics and electrical things already taken into that. Okay, and then look at cars. Cars used to be a mechanical device. Remember those ambassador cars, which is like very steel body machines? Good luck finding them these days, because these days the cars that are modern is all software. If you take Tesla cars, they're completely electric, and it is all powered by electrical motors. And guess what? Everything is controlled by a software. It's no longer the cars is no longer a mechanical device. Instead, it has become an electrical, electronics, computer science combined kind of a device. So pretty much you can call them as a mechatronic kind of a device. Okay, which is interesting. So that's the again, if you take an example of the Tesla cars, they're basically DC drives. They have sensors all over the place. They have LiDAR. They have computer vision technology. They have cameras. They have different kind of capabilities, and they can do autopilot mode, which means they can drive by itself. And the most important thing is they can be personalized. So the moment I get into the car, it actually knows it's me. And then because of that, I have my settings. Okay, for example, I have my seat height. I want somehow my steering wheel to be in a certain position. I want the AC to be on when I get in. I know my optimal temperature. It all knows all by itself. So that's why it provides a personalized services. And here's an example. The moment I get in, it knows that I love Adele, and then it actually plays from my Spotify, and it knows exactly where my home is, where my work is. It gives you a lot of updates on the go, which is all possible because of this data that we actually share, and then the data that we actually use to build these kind of technologies. So coming to the electrical engineering, the microgrids, which is very interesting, given that we already talking about being energy independent. We no longer want to pull the power from the grid. Instead, we want to own our own grid, and then we probably like join hands and then probably use it for our own beneficial things. And that's exactly where Tesla is also going. Okay, they a lot of their microgrids are powered by Tesla power adapters, and they also have a variety of products in the space. Electrical appliances. So if you think about those incandescent halogen kind of a light, these days it's all replaced by there's electrical devices which has a lot of electronic components in it. So the typical example I can actually give you is Philips Hue. So where you have an app and you can actually choose the color you want, uh, depending upon the the persona of your house or the mood in which the family actually operates, and they're very energy efficient as well. So again, all these electrical devices has become electronic devices, okay, or electronic infused into it. Okay, so the key takeaway in the first session I want to give you is the electrical machines that we have around us are generating massive amount of data. And the real value for electrical engineers is in terms of that data generation from all these electrical devices, be it a car or a smart home or a microgrid. The value delivery for electrical engineers is in the device monitoring. Okay, when do you think this electrical device is going to fail? Okay, it's very important. Then understanding customer behavior. To give you a perfect example, like if you take a smart home, and then let's assume that you wake up in the middle of the night, okay, and then it actually knows the pattern of you waking up at some point in time in the night. Then instead of blowing the light at 100% luminosity, you'll actually do it at, let's say, 40% luminosity. Why? Because you are already in a sleep state. Okay, if it blows at high luminosity, probably you'll come out of the sleep state. So it actually knows all the things. I'll actually put the yellow color or lights on instead of having a white light. So these are all like understanding customer behavior and then tweaking the system controls basically. And it actually does a lot of trends and pattern analysis. Okay, let me break. Any questions? So the first session, I've actually given you a high level idea about data. In the next session, we'll dive into AI and ML. But before that, I just want to take a pause. If there's any question, put it on the chat window. I have to answer. Okay. All right. So there's no questions. Let me move on. Cool. So this is an interesting. So this session, second session, is more about AI, particularly AI and ML. So AI is an umbrella term. Artificial intelligence is a very umbrella term that comprises of everything in the world, where every algorithm, every new technology comes under that AI. The basic definition is any kind of a system that can show some characteristics of being intelligent. Okay, the intelligence comes from data, and if it does that, then we call this as an artificial intelligence. Why? Why it's artificial? Because it's not a brain, which is powered by biological tissues, and it is very human. And that's why it's not a human intelligence; it's an artificial intelligence because all the intelligence is produced by this silicon-based entities. So it's very simple. So the process of doing this in electrical engineering discipline is very simple. So you have things, basically it does sensing. So you can actually think about any kind of phenomenon that actually occurs in the world, temperature, humidity, wind speed, your voltage, current, frequency, your phase angle. You can think about any kind of a physical entities, physical phenomenon where you need to capture. As as long as you have some kind of a sensing device that can actually produce some data, you can actually send it to the world for pretty much processing. So in terms of electrical engineering discipline, so a lot of the data we actually dealing with is analog in nature. Okay, so in order to process them by the computer and also for these algorithms, you need to digitize all this analog information. And you probably know a technique called ADC, analog to digital converter, which actually does that. And then you store them. Basically, has to be some kind of a big data platform where you actually store all those data in the digital form. And that's exactly where you throw the compute power. Okay, and that's where you do a lot of algorithms on the top of the data. The reason why we moved to the cloud is because if you have, let's say you have lots of data and then assume that you have 100 gig of data, how are you going to load them in the laptop? Physically not, is not possible. Nobody has 100 GB RAM in our local laptops or desktops. So that's why the cloud offers scalability, and you can avail a lot of compute power as well as scale. And the important thing here is, in terms of this process, how do you actually automate the decision? That's very important. And that's exactly where a lot of these companies, they provide a lot of services, basically. Okay, so this is the typical AI architecture in terms of how they think about the electrical engineering. So in the bottom of the pyramid is usually you have like sensors and actuators. That's the lower end of the pyramid. And then you have some kind of connectivity, basically, to the sensing agent. It could be anything that's local, like Bluetooth, NFC, and stuff like that. And then the next layer is your gateway. Basically, you need to take the data from those sensors, and then you have to send it to the cloud through some kind of a gateway technology, something like a GSM or Wi-Fi technology. Then you have your management services. That's exactly where your cloud and data security, those kind of aspects comes in. Then you have the application layer. That's exactly where your mobile phone apps or desktop apps or any kind of a software that you use actually sits on the top. It's very simple file level kind of an architecture. And the most important thing is they are all coupled together. Okay, you can't eliminate one piece of stack all the 5 stacks are extremely important in terms of building that intelligence. Okay. So at the end of the day, the moment you produce sensing, you have some electrical signals, it gets converted into data. And then you only deal with the data, which is a digital entity. Okay, let's look at cloud. Why cloud? I know it's a little bit of a computer science for electrical engineers, but basically you need to understand this concept called cloud. Why cloud? So cloud is basically, it offers scalability and elasticity. I'll tell you what it is. Scalable, for example, if you bought a laptop and then you have an Intel processor in it, and then let's say for your processing, you need a higher end computer. So basically you need to replace that laptop or take a laptop to the shop and then take that Intel chip out, put the new motherboard in, and then you have to come home. Okay, so that's usually but in the cloud, you can actually provision those kind of machines at will, at scale. Let's say you want 10 of those machines, you can actually provision them. So that's the elasticity part of it. And the other thing is the storage. And our laptops and hard disk are limited by capacity. You can actually store only certain amount of storage. But when you go to cloud, literally it's infinite. Okay, you can actually store billions and billions of files, gigabytes and petabytes of data, no problem. Okay, so that's the most important thing. And the third aspect is the software. So let's say you want to run a software at that scale and you want to test it, it's only possible in the cloud. So that's why most of the companies, they actually go to the cloud. So let me ask you the question. What is the device that you hold that has some sensors and connectivity and internet gateway on it? So type your answers in the chat, please. So what's the device we hold that has some sensors, connectivity, and an internet gateway? So what do we actually have? Any guesses? Anybody in the chat window? Okay. All right, let's move on. So the answer is smartphones. Basically, the smartphone is the one that we have. And the important thing about this is the data is the raw material for intelligence. The more data we actually produce, the more intelligence it can actually mine. Okay. Thank you, ma'am. Somebody's typed mobile phone. Yeah, it's right. So the more data we actually produce, the more it's a raw material for intelligence. And the data is the currency these days. So to give you a perfect example, let's say you buy a new mobile phone. What's the first thing you do? You say, hey, I want to migrate the data. Okay, so you want to migrate the data, not the apps. You just want the data. Okay? So the data is the primary factor here. So in terms of AI, I just want to give you a high level idea about what an AI can do. So the machine learning is a subset of AI. So it's another umbrella term. And the computers, given the data, it can only do 3 things really well, and that we call it as a machine learning. It can only do 3 things really, really well. The first thing is it can do forecasting. When I say forecasting, the forecasting is all about using the past data to forecast or predict what's in the future. To give you a perfect example, the weather in the next 1 hour depends on what was the weather like an hour ago or 2 hours ago or even yesterday. Okay, because the weather depends on the past behavior. So that's forecasting. And there are many algorithms in machine learning to do some forecasting. The typical thing that we actually seen is called linear regression, and the other one is neural network. So those are the typical kind of an algorithm for forecasting. And the second thing a machine can do intelligently is called classification. Okay, assume that you actually show a picture of a mango and a potato to a computer, and then you show 1,000 images of mango, and those are like labeled data. Basically, you tell, hey, show all the mango pictures, and then share some mango, and then you show potato, and then you show thousands of images to the machine, and then it's able to classify which one is a mango and which one is a potato. Okay, let's say you give a new picture that contains any of those fruit or a vegetable, then it's able to classify them basically. Okay, so that's very easy to do, and usually the classifications are called as supervised learning, because you label the data and give it to the computer for actually recognize. And the typical kind of algorithms you see called K-means clustering, random forest, and naive Bayes. And there are a lot more algorithms. I just only given you a few. And the third one is a very interesting thing in machine learning called pattern recognition. And it's also called as clustering, or sometimes in machine learning or statistical terms, it's called as unsupervised learning. Okay. So what we're trying to do is we just throw a data at the computer and then ask it to figure out what kind of underlying patterns are there. Okay. And we're able to do that. And we also have support vector machines, and there's a lot more algorithms that can actually do clustering basically. And this is all an AI or an ML can do, only these three things. Now, given that you probably know about ChatGPT, yeah, so ChatGPT, I'm pretty sure you have actually used it. So in what kind of category ChatGPT actually falls in? Type your answers in the group chat, please. So does it have falls in forecasting, classification, or clustering? So the ChatGPT technology, what um, category does it actually play? Put it in the chat window, please. And ChatGPT is a nifty technology. Again, it's not applicable to electrical engineering, but it's being used by everybody in the world. I'll give you a couple of seconds for you to actually type in. Okay. Okay. So the ChatGPT kind of technology falls in the group called forecasting. Okay. And you might be wondering how it's forecasting. Basically, it's actually predicting the next word. So a ChatGPT is a big or a giant autocomplete. So that's what it is. So it actually falls under forecasting. Cool. So let's dive into this few of this. I don't want to go deep into some of the mathematical fundamentals, but enough for you to actually follow up on some implication of the smart grid, which I'll touch in another 5 minutes. So if you do forecasting, basically you probably seen this equation called y equal to mx plus c, and that's the classical kind of equation that we studied in our mathematics during our school days. And basically what you assume is you assume there are a lot of variables and you have one output variable. Okay. And basically what we're trying to do is we're trying to do some curve fitting. Okay. And one of the technology that one of the algorithms that's used to do curve fit is called least squares. Okay. And it is very easy to solve and deploy. The model is also very easy to understand. Basically, you write this equation as the output variable as y equal to a times x1. So the x1 could be a variable. Let's assume that's the voltage. B times x2. X2 is like current. And C times x3. X3 could be frequency, and it goes on. Basically, your output could be what is the power generated by a generator in the next minute or next second or something. Okay. And basically, it's solving all about matrices. Basically, it's in one hit you can actually solve this bulk of this equation in just one single line of command. Okay. And that's linear regression for you, which is used for forecasting. Again, we also have neural network. I won't go into detail. Basically, it has all this different layers, and you pass it on, and the computer actually learns the weight of these layers, and then that helps you to predict. So it's a lot more flexible in nature, because if your inputs are not linear, sorry, if your independent variables are not linear, then you actually think about neural networks where you can actually map some nonlinear relationship as well. So the next example I want to give you in terms of classification is called um, k-means clustering. Okay, so basically you have to create this cluster, and then the way you actually do that is you take your whole. Okay, so the typical use case for electrical engineers is assume that you have electricity consumption data from different segment. For example, one from consumers like houses. Next could be industries. Um, and the other could be EV charging stations and stuff like that. And then you have this huge data. Assume that it's all across Tamil Nadu, so which means you'll be sitting in the wealth of data. So then you need to map what is the characteristics that actually is for consumers. Okay, based on the date of the time, day of the day, and then the consuming pattern of power actually varies. Okay, and then you can do some kind of feature selection. We use something called principal component analysis, which is basically an eigenvalue and eigenvector kind of computation, and then you basically cluster them. The cluster A, cluster B, and cluster C. Okay. The reason we want to classify is, let's say a new data point comes in, then then a new provider gets added in. Okay, and then we can actually classify which cluster they actually belong to, which let me give you a perfect example of how this is actually used in electrical engineering. So earlier I've actually shown you that if you have all this consumer power consumption pattern, then you actually classify them. Assume that you have a new someone actually asking for a new power connection or electricity connection, and let's assume that they say that they are from household. Okay, so you actually put some different tariffs and actually give them a connection. Then you found that they actually, based on the consumption pattern, you actually found them they are in cluster B, which is for industrial, which means they are actually forfeiting the system. Okay, they're actually cheating the system. They actually catch them, saying that they got them in the house or domestic connection, but they are actually, the consumption pattern actually shows that they are actually in the different cluster. So that's how people actually find non-compliance kind of connections, which is interesting. Again, the other aspect is the clustering part, where basically if you look at the left side, you have this original unclustered data. You don't know which kind of pattern it is, and you give it to an algorithm, and then it actually splits into the clustered data. Now you can actually see it actually groups them like red into one cluster, blue into another cluster, and green into another cluster. Okay. These are very hard problem to solve. Again, there are a lot of algorithms that's been put forward to actually solve this problem. Um, so a supervised learning is basically you give a label data. And unsupervised learning, you don't give a label data, but it actually learns by itself. And in electrical engineering, there are a lot of things you can actually do with this kind of analysis. For forecasting, for example, you want to know what's the demand of electricity in the next hour in Coimbatore. Yeah, forecasting algorithm is going to help you. Let's assume you want to find out some kind of an anomaly. Let's say some kind of an electrical grid failure or some kind of a component failure. You can use mathematical algorithms to find out anomaly. Again, the clustering use case I've actually given you is you're trying to do some compliance kind of an activity. Okay, so this is the end of my session 2. So in terms of the learning, what I've actually shown you is a lot of standard algorithms exist for these three things: forecasting, classification, and pattern recognition. And if you're really interested, there are a lot of vendors, cloud vendors like Microsoft, Azure, Amazon, AWS. They offer a lot of these algorithms out of the box. Basically, you throw the data at the cloud, you store them, and then you actually call all these algorithms in one line of command. If you're really into Python, I'm not sure how many of you learned and used Python. So there is a nice little package called Scikit, and then you can also use TensorFlow from Google as well. So those are actually used to take these algorithms and then operate on the data that you have. Okay, so I think we are nearly halfway there into the program. Just take I'll give you 30 seconds. If you want to have, if you have any kind of questions, type it in the chat, and then I'm happy to answer. I'll give you 30 seconds starting from now. The first session I covered about data, how data has been generated, how it's been stored. The next session, session 2, I will actually give you overview about the AI. Then next is the crux of this, the main crux of this workshop. Then we'll go into the smart grids of how do we take AI and ML. Few seconds. Yeah, no questions. Okay, let's move on. Okay, so there's a question. Is there any limitation for data sample for algorithms? Yes, sir. There is always a data. So basically, the more data we have, the better it can be utilized for algorithms. So in terms of applying algorithms, for example, linear regression, you can even apply the linear regression algorithms on 10 data points. Okay, there isn't any kind of a data set. But having said that, if you have more data, then your forecasting will be a lot more accurate. So there is a dependency on the number of samples with the accuracy of your forecast as well. And then more importantly, the algorithms, if you want some adaptability in terms of the algorithm as well, so you need more data points. Okay, so what number? So in terms of the exact empirical formula, there isn't any, but having said that, if you want to do some linear regression, again, this is from my own experience, you at least need to have like 30 samples to make some kind of a linear regression model work. And then that has some statistical significance in it. Okay, the minimum could be like 29 or 30. Again, it's a known rule in the world of mathematics. And in terms of the other kind of algorithms, I am not sure. Okay. Okay, let me move on. Thank you, sir, for asking that question. Okay, let's come to the important aspect. Smart grid. So, and you probably know what a smart grid is. It's basically a system is intelligent in terms of understanding the power generation part, understanding the power consumption part, and it can also make some intelligence decision on the top. And you have this amazing systems in place, some kind of a control system in place. So in a nutshell, this is how I view it in terms of a smart grid. Basically, you have power producers and power consumers on the one end. These are the components of your smart grid. The power producers, they can actually vary. I'm trying to mute. Okay, so the power producers and power consumers, they actually have different kind of characteristics. So power producers, usually they are your traditional coal powered, then you have hydro, you have windmill, and you have solar, and you also have nuclear. So those are typical kind of a power producers, and they set basically, and they but the consumers, they're also different. Household, you have industrial, you also have this EV charging stations, and you might also have some kind of a heavy machinery kind of an industry as well. So those are typical kind of consumers. And the other is intelligence from data. Again, when you have sensors across your power producers and consumers, you get a lot of data, and then you're trying to make some intelligence out of it. Okay, so that's the another component in your smart grid. And the third important thing is, what do you do with intelligence? So the intelligence we can only exhibit intelligence when you act, basically, and that's exactly where the control systems comes in. So these are like your SCADA systems and other kind of systems hooked to the cloud, or some kind of a machine learning algorithm that actually tells you what to do. Okay, so that's a typical kind of a component of a smart grid. And it's very important to actually understand the characteristics of power producers. Let's start with power producers. So the first is ramp up and ramp down. And I'm not sure how many people actually visited one of those coal-powered power plants. So basically, they have this huge turbines and machineries where you put a lot of coal, and basically it can actually spin very fast and can actually try to give you a throughput when you throw a lot more coal at it. Okay. To give you a best example, let's say you're connecting your coal-powered power thermal plant to an industry. Okay, so assume that the industry needs a lot of power because they just want to turn on a big molding machine or some kind of machine that has to draw a lot of current or electricity from. So in that case, it will try to draw more electricity from the grid. Apparently, your power producers is not unable to supply it. So what actually happens is your frequency actually fluctuates, and then actually brings the power producers um, to non-compliance, and maybe damage a lot of these electrical equipments. So in that case, so once the power demand is there, the power producers have to ramp up. Okay, so basically there's some kind of a system feedback, and then basically they actually throw more coal at it and actually spins off. This turbine runs off, and within 1 or 2 seconds, it can actually produce few kilowatts of electricity, okay, within few seconds. So that's the ramp up and ramp down. Again, and the other in terms of ramp down is, let's say somebody's using a lot of refrigerators and stuff like that, and at 6 p.m. everybody shuts down. Okay, again, they have to ramp down their production. So it's a very important characteristics of ramp up and ramp down. And the second is in terms of seasonality. To give you another example in terms of power producer, if you look at windmill, they're very seasonal. They can be only active when there's a wind flow, and that's very seasonal pattern as well. Again, with the solar, it's very predictable. As long as the sun is out and there's no cloud cover, you can generate the electricity. Those are very seasonal characteristics. And the third aspect with the power producer, sometimes some of the power producers are very stable. If you look at nuclear, you need a minimum kind of a demand for to turn on the nuclear power plant. Okay, so those are very stable kind of system. So again, what kind of data we can actually capture in the data generation part? So if you take a typical kind of a intelligence layer, and then basically what we really want to collect is current, how much current is being produced, your voltage, your power, which is pretty much the multiplication of those two parameters. Then you want to calculate frequency. You can look at phase angle. You can look at power generation. You can also look at other parameters as well in terms of the data generation. It's not limited to these four main parameters. You can actually calculate how much coal being put into the coal power plant, what is the vibration of those turbines. You can actually capture as many data points as you want. Okay. And then basically it's very simple. So once you have all this data, you convert those analog signals into a digital form, and then you actually put it through some kind of a connectivity channel, and you actually stream it to the cloud. So basically these are all this current voltage ends up as a data point in your Excel spreadsheet, basically. Okay. So where you store, and you store and you do the analysis basically in the cloud. And that's exactly where you actually run your machine learning model on the top of the data that you actually collected. Very simple. The paradigm is very simple. You act locally using local intelligence. Okay. But having said that, to mine the intelligence, actually store it to the cloud. The reason is The reason is very simple. The cloud offers unlimited storage and compute power, and it can run powerful algorithms, but your local intelligence cannot do. For example, a SCADA system cannot run thousands and thousands of mathematical computation. Okay, it's not built for that. And it can, but having said that, once you have intelligence, then you actually act at the local area. And it is the main important characteristic of electrical engineering data, and which is very interesting and in fact very close to my heart, because they are time series data. Every single data point that we actually capture in the electrical engineering, there's some kind of a timestamp. The reason there's a timestamp is because you're dealing with current and voltage, which are different on time. Okay, and every time you stream any kind of data to the cloud, basically you actually send the time along with it. And they also exhibit seasonal patterns. Okay, in terms of producers and consumers, there's always some seasonality present. For example, I give an example where the solar power plant, they exhibit seasonality. They can only produce power in the daylight and no cloud cover. In the night, they don't. Okay, um, with the windmills, it only produces when there's a wind flow. Okay, so there's some kind of seasonality. In terms of consumer behaviors, assume that everybody gets home and then they turn on their fridge or aircon at 5 p.m. in the evening. Okay, so that's the seasonality of consumers basically. And what it actually gives you is, given these two time series and seasonality patterns, we can actually predict what data is gonna come next, basically. And all the algorithms actually given you, for example, linear regression is one, and you have algorithms called ARIMA, ARIMA, autoregressive moving average, and you have SARIMA, seasonally adjusted ARIMA, and you have a lot of other algorithms which can do forecasting. Okay, let me give you some kind of a use cases where it's very apt in smart grids. Okay, so I want to go in depth into one of these use cases. Given the unpredictable consumer behavior, how can we predict frequency variation? Okay, and you probably know from your industry standards, the standard operating frequency in electrical device in India is about 50 hertz. And okay, type in the chat, do you know how much variation they actually allow? You know how much variation they actually allow in the 50 hertz. So how low can it can go and how high can it go? Put it in the chat, please. Anyone? Do you know how high it can go? So they allow about 1% deviation. Okay, okay, 49.2. No, I don't think it can go to 49.2. I think it can go to 50.05 and 49.95. Okay, they allow only 1% deviation. The reason is, if it goes beyond that, then all your electrical appliances will fail. Okay, and they allow only 1% deviation, plus or minus 1% deviation. So that's the standard deviation we're actually talking about. Okay, so the typical use case is here is, so let's say you are producing 10 megawatt, and then the consumer is actually consuming 10 megawatt, no problem. There's no frequency variation. Assume that the consumer is trying to draw more power from your grid, more than 10 megawatt. Then the frequency will actually, what happens to the frequency? Does it increase or decrease? Decrease. Okay. So if a if a consumer is trying to draw more power from your grid and you're not able to do, the frequency actually increases. Okay. And it's the other way around when you have the other. So when you draw more, sorry, when you draw less, but you have more bit capacity. So this is a typical kind of a problem in the smart grid. Okay, can we predict the frequency variation based on the consumer behavior? Again, you have thousands and thousands of data points. You have millions of data points when you apply smart grid across India. How do we predict um, how much the frequency will vary at what point in time? It's very important. We can also do that. Okay, it's only can be done at scale. So that's one of the typical use cases we have actually seen in the smart grid, where we actually seen electrical engineers working along with this data scientist to come up with the right algorithms to actually predict the frequency variation. Okay. And the next important thing is, can we forecast demand, the power demand for tomorrow, for next minute, for next hour in a particular city or a particular suburb in a city? We can also do that. Okay, it's very easy to do. Again, I'm giving you an example of a simple algorithm called linear regression or a moving average. They can actually forecast. So the most important thing in the forecasting is how do we get it right? So the accuracy actually matters. So the accuracy can only increase when you have a lot more data point coming to your cloud and then applying the algorithm on the top. And then every single day, the TANGEDCO, the Tamil Nadu Generation Authority, they actually do some demand forecasting for the next hour, the next day. So they know how much to provision infrastructure, basically, their power generating infrastructure. Assume that a rain hits some power generation, obviously that will go down. We can't have blackouts throughout a particular city. So obviously they have to provision a new kind of services or new kind of power generation unit. They have to know the demand. Okay, so that's a very typical kind of use case we see in the smart grid kind of technology. The next aspect is very close to my heart. I've been on many. I've worked in a company which actually does this forecasting for power generation, um, and I visited many power generating coal powered generation unit. And this is a typical problem. The second use case I'm going to give you is the problem that actually exists in the industry at the moment. The problem statement is very simple. Given the power generation routine, there is thousands of machines, correct? The electrical equipment that actually run. They're mechanical devices as well. So they're just turbines or thermal units and stuff like that. And they can't run forever. So they need to be shut down for maintenance. Okay, they should be scheduled maintenance because there's a wear and tear. Maybe you need to replace an oil or you need to replace some rubbers or bearings and stuff like that. How do we ensure we optimize the maintenance schedule for thousands or millions of equipments across India so we don't disrupt the power generation? So very hard and one of the typical use cases in the machine learning in the smart grid space. Okay. And again, there are a lot of algorithms to do that. Again, it's a mixture of doing a lot of classification and also forecasting as well. So there's a lot of work. You need to come up with a sophisticated algorithm to do this. Okay. And the third aspect in power generation is in India, yeah, we grow in terms of population every year, which means ultimately the power capacity also need to grow. Does it need to grow linearly or non-linearly? That's again something we need to understand. So as the power generation requirement or demand for actually grows in a particular suburb or a particular district or particular city or a state in India, they need to provision new capacity. And they have to determine what kind of capacity it should be. It should be a nuclear or thermal or a wind, and how much they need to provision and when. And the answer to all this question can be given out by a machine learning algorithm. That's very easy to actually understand. That's a typical use case we have actually seen in the smart grid space. The next aspect is the anomaly detection. You have to forecast what an anomaly is. Basically, an anomaly is more like an outlier. If I give you a 100 data in an Excel spreadsheet, and I ask you to find an anomaly or an outlier, it's very easy to do. Basically, you calculate the standard deviation. So any data point that is that is 3 standard deviation away from the mean, you call them as an outlier. Or if it's 3 standard deviation below the mean, you call them as an outlier. It's a very rudimentary kind of a method in mathematics to find out an anomaly. But having said that, it can't be applied to an electrical signal. Okay. The reason is they are they exhibit mostly they're stationary. But having said that, there's a lot of nonlinear components actually added over a period of time. So you need to apply a lot more sophisticated algorithms to detect an anomaly. Okay. Okay. So okay, let me skip this question. Okay, so the other aspect I want to talk about in terms of this AI in smart grid is it's very important to actually understand what is causing what. Okay, they are called as causal variables. So it's very important because understand that then you'll have some kind of a statistical significance in terms of coming out from this AI, the machine learning algorithms to justify your outcome and insight, basically. So here's an example I've actually given you. This is one of the typical data in terms of battery charging for an electrical bus, and when it actually charges, how much it actually generates, regenerates electricity when it's at idle state, how much it actually consumes, how much kilometer actually drawn, and stuff like that. So it's a typical kind of a data set actually seen. These are some of the data sets. Again, if you're really into smart grids and you want to get access to the data, and there is an Indian government portal called India Open Data Portal. Its website is data.gov.in, and if you type something like smart grids, there are thousands and thousands of data sets available from the Indian government. Okay, for different regions and geolocations. They also given out a lot of data in terms of historical data. They actually pump out. So that's something you can actually use. And there is also called data.world, where you can actually search for a lot of the smart grids. Again, there's a lot of Internet of Things devices data that can be used in your projects and stuff like that. Again, if you want to test out, you just download this data into your Excel, and then if you install anything, something like Python, or you can actually use something called the Google Colab. You can actually play with all these algorithms and then trying to do some forecasting, classification, or clustering, or even address some of the use cases actually given you. So this typical use cases you can actually try to solve with some of those algorithms as well. Look, that's pretty much the content I have for you. Thank you so much. And I now open up for questions.
Participants, you can unmute and ask the questions.
So I've covered mostly on the consumption and power producers consumption, not pretty much on the distribution and even on the storage. Those are, yeah, gold mines for data actually, and you can actually do a lot more things with it. Okay, which optimization technique is easy? I can work with EV. Okay, so in terms of electric vehicle, there are interesting use cases, basically. We want to optimize the store, optimize the energy charging. Let me give you an example. Let's say you bought an EV vehicle, let's say the Tata EV or Tata Nexon, and then you start to 100% capacity and you start driving. Okay, great. So, and there is a the lithium ion battery, they also degrade over a period of time. They can actually only do 10,000 recharge cycles or things like that. But having said that, you also want to go and reach a place which is beyond the range of the current capacity of the your battery. So you need to have some kind of an optimization algorithm that actually tells you at what point in time or what distance you have to recharge the EV to what percent. It's extremely a typical optimization problem we have, and there are a lot of algorithms. There's a lot of dynamic programming optimization algorithm. There's some that you can actually use to apply all these things. Okay, cool. So there's one more question. What methods are used to handle the missing or incomplete data when training AI models for smart grid? So in terms of missing values, there are many pre-processing or techniques available. One of the typical examples, especially that applies to the smart grids, is you can just do extrapolation, which is basically an average of, let's say you have let's say you have 3 data points and the second data point is missing. Basically, you take the average of the first and the third data point. Okay, so usually that you can actually do something like an average mechanism. And there are other places where if it's you can use median and you can also use mode. And those are 3 simple kind of statistical techniques used to fill missing values. But having said that, there is a lot more sophisticated algorithms available to find the missing values as well. But that's a typical pre-processing step which we do, ma'am, before we train an AI model. Okay, so in V2D technology, yeah, frequent charging and discharging is required. Absolutely, ma'am. I completely agree. So yes, so a battery, currently the lithium ion batteries, they degrade over time, and you've probably seen from your cell phones as well. If you bought a cell phone after 2 years, the charge does not hold. The reason is the lithium ion battery can only do so much recharge cycles. I think it's about 10,000 cycles, depending upon the manufacturer you get it from. Can you optimize when you have to recharge to certain percentage? Absolutely yes, because the lithium ion performance, lithium ion battery performance depends on a lot of parameters, and one of the key parameters called temperature. So if you play with the temperature, you can actually try to maximize or squeeze most out of those lithium ion batteries, and that is a typical optimization problem. And if you buy an Apple iPhone, they actually figured it out. There's a small algorithm that runs on the chip on your device that actually optimizes your charging cycle. Okay, and that's a very good, if you collect the data, ma'am, and then I'm pretty sure you can work on this problem. It could be a good kind of a PhD thesis problem to solve. Any questions before I wrap up? Okay, before I close, I just want to give you few tips, given that most of you are from electrical engineering background. So to apply ANML in electrical engineering, it's very unique. The data scientists or computer science people cannot do it. Only the electrical engineering people can do it. The reason is you are the domain expert, okay? And it is very easy to learn computer science skills. For example, if you want to know, do some machine learning, all you need is Python. You need to learn Python as a programming language, and all this machine learning algorithms, a basic of how this machine learning algorithm works, what are the input parameters, what are the output parameters, and how do you do with this all this outputs that you get. Okay, so that's the first and foremost thing you have to do. Learn Python, learn a little bit of a programming language, learn about all this ML algorithms are actually giving you things. Then you bring all the data from your domain. For example, smart grids or any battery technologies or any kind of technology that you actually work on. Bring those data, apply those algorithms, then you'll get the result. Then you actually apply the domain knowledge to get a lot more insights into how it actually being used. And that's the power I am actually seeing with this electrical engineering discipline. You have to learn some kind of a computer science discipline, and then you have the domain knowledge. With that, you become a lot more powerful, a lot more valuable in the organization and also in the research community. And I'm pretty sure a lot of the papers that you write can actually help to get published in this high impact journals when you combine your domain knowledge with this expertise from mathematics and statistics. Yeah, so that's pretty much I have. Thank you so much for attending, and then I hand over to the organizers. Thank you so much.
Thank you, Selvaraj sir. Deepika?
As we conclude this enriching session, I take this opportunity to express our heartfelt gratitude to Dr. Selvaraju Murugesan for sharing his invaluable insights and experience. Your thought-provoking words and profound knowledge have truly inspired us all. I also extend my sincere thanks to all the participants for their active involvement and enthusiasm. Events like this are successful because of your curiosity and dedication to learning. Finally, I express my sincere gratitude to the institution for making this event possible. Let us carry forward the knowledge and ideas shared today into our future endeavors. Thank you all. Have a great day ahead.
Thank you, sir. Selvaraj sir?
Yeah, thank you. Thanks.
Thank you, sir. The feedback will be shared shortly, and the next session will be starting in another 5 minutes. So participants, please do stay back in this same link. The feedback link will be shared shortly.
ಈ ನೂಲ್ ಸಿಂದೆ ಸರ್ ನೂಲ್ ಮಟ್ಟ ಬಚ್ಚಿ ಕರಾಕ್ತ ಹಂಗ ದರವ ಇದರಿಂದ ಈ ನೂಲ್ ಮಟ್ಟ ನೂಲ್ ಬಚ್ಚಿ ಕಡಿವೆ ಸಿತ್ತ ಅಲ್ಲೇ ಸತಾನೆ
Good evening, sir. Mayavanan here. Am I audible?
Yes, sir. Yes, sir. Good evening. Sir,
Good evening.
thank you. Thank you so much.
Thank you.
Yes, sir. We can start, sir. So I call upon Sudarshana to give the introduction about the resource person for today.
Good evening, everyone. I am Sudarshana from Electrical and Electronics Engineering Department of Sri Krishna College of Technology. I welcome you all to the fourth session on day 2 of the Faculty Development Program on the topic Cyber Physical Systems in Power Engineering, bridging the gap between Industry 4.0 and 5.0. It is my privilege to extend a warm welcome to all of you to this special session. Today, we are fortunate to have with us a distinguished personality, Mr. Mayavanan Megavanan, industrial veteran and a thought leader in cybersecurity, cloud security, and IT infrastructure services. With an illustrious career spanning over 36 years in the IT industry, including 21 plus years of remarkable contributions at Tata Services, Mr. Mayavanan have significantly impacted IT infrastructure services, strategy formulation, and delivery excellence. As an information and cloud security auditor, his expertise in CSA, CCSK, ICCA, CCAK, CISM, and CRISC certifications, coupled with his practical knowledge, makes him a guiding force for aspiring professionals and seasoned experts alike. With a profound mastery of information security and risk management, he has spearheaded global initiatives, adding over 50 global customers to TCS IS shared services delivery units. His contribution in cloud security, business continuity planning, and disaster recovery management are unparalleled. Currently serving as a professor of practice in cybersecurity at Jerusalem College of Engineering and an edutech consultant for CyberFort DigiSec Solutions Private Limited, he continues to shape the next generation of cybersecurity experts. His role as an auditor, risk manager, and strategic consultant has brought numerous accolades, including the Best Internal Auditor Award and recognitions for audit in ISO standards and GDPR compliance. Today, we are privileged to gain insights from his vast experience and profound knowledge. Ladies and gentlemen, please join me in welcoming our resource person, Mr. Mayavanan Megavanan.
Thank you, ma'am. Thank you. Thank you all. Can we wait for some time or can we start now?
Yeah, we can start, sir.
Okay, thank
We
you.
can start screen, sir.
I hope you are seeing my screen and the voice is okay. My video is okay. Can I switch on the video or I can switch it off? If you
Okay, sir. Okay.
right, thank you. Thank you all for joining the session. Next 1.5 hours from now, we'll quickly look at the various aspects of how the industry 4.0 is transforming itself to industry 5.0 and how our physically we are going to talk about the CPS, cyber physical system, and how CPS in power engineering, which is going to help in terms of transforming industry 4.0 to 5.0 using some of the examples. We'll take it up on smart grid and all that, right? So we'll look into that. Thank you all for joining our session, please. Let's move on, right? Right. This is the overall topic of that. So if you look at this particular overall topic, we are going to talk about 4 or 5 different terminologies, right? One is smart grid. The smart grid itself is one major subject in Masters of Engineering or ME or in BTech. That is one full subject itself, right? So we cannot cover that entire smart grid in 1.5 hours. But the essence of what we are going to talk about it is how the smart grid is going to adopt your industry 4.0 and transform itself to industry 5.0, adoption of industry 5.0, right? And we have to talk about the sustainable, the word called sustainable, right? It is very, very critical word now, right? We are going to talk about the 17 goals for the UNICEF's sustainable development goals. Out of that, 4 or 5 specific goals are related to power system, right? So we will talk about that. how power systems are going to make use of the four out of 17 goals of sustainable development goals of UNICEF. This is what we are going to talk about in next 1.5 hours, right? So in my topic from this particular topic is particularly industry introduction to industry 4. Okay, next one, right? Cyber physical system power engineering, bridging the gap between industry 4.0 and 5.0, right? This is what we are going to talk about now. Let's look at what are we going to talk about. I have referenced multiple, the organizations, and I have given a reference. I hope this PPT will be shared to all the participants sooner or later, right? There are some of the websites where I referenced where the materials have been taken. I have given a reference here. Let me look at, I'll tell you which are the very, very critical websites which are very important for adopting Industry 4.0 as, transforming itself to Industry 5.0 in power engineering specifically, right? So all of you know some of the website already, right? So NPTI is the Government of India National Power Training Institute, which offers a course itself in power engineering related thing. Central Power Research Institute in Bangalore, which is also contributing various aspect with respect to smart grid and other things, which is south of Bangalore, I think. The grid controller, which is very, very important, where we know we can track what's happening in India, what are the daily loads and all that, right? It's a huge data which is producing Government of India website. Let me actually get into that website before we understand, right, what are we talking about, right? So if you look at this website on a daily basis, you get monthly report and all that. A huge volume of data is collected, right? How are we making use of this data to predict or project the future trends, right? So if you look at the daily report, I just downloaded the two reports, which are yesterday's December 1st of December report. I just open it up and then just understand what are we talking about, right? So if you talk about, there are 5 regions in India which is producing so much of a megawatt of things like that, and which you see the percentage of energy which is generated through multiple means, right? Hydro energy, wind energy, solar energy, right? If you're seeing that, they are giving in terms of the percentage, right? How much percentage is contribution why the energy shortage is as of now. On yesterday it was 0 overall. Around 0.21 megawatt was eastern region, there was a shortage. Other than that, they were able to meet the complete requirement for yesterday's requirement. So this is a daily report, right? So weekly report, monthly, entire trend, it's also they are giving it. Let me look at what contribution they are giving in terms of the percentage, right? So if you look at this, coal is contributing to the major, 75% of our energy, electricity is generated by coal. The rest of the energies are wind power, solar, biomass, and other. That is the second one, right? 13%, which is going to increase further. So, which means our smart grid is the only solution to transfer two-way transfer of electricity between the producer and the consumer, right? So the organization which is governing the entire transmission of the power across India, which is the governance body which is controlling the transmission, production, transmission, and consumer getting the related power and all that. So they are able to meet on a regular basis. They are continuously monitoring all that. So if you see that, if you think that big data analytics is going to help organization like this, right? The day on which it is what we are seeing is after they analyze all that, they put just a report which is giving you this much information. By the time they collect on a daily basis, a huge volume of data are collected, right? In terabytes of volumes of data are collected, that is getting processed, right? So if you look at the monthly report from them, right? If you see the monthly report also, it gives you the entire report how much they are consuming, what is the production, what is the project, everything which is been published here. So that's what I just wanted to talk about, that particular website, which is going to give you, it's a very, very important website. It is the grid controller of India, right? Similarly, other power grid corporation, right? The International Renewable Energy, IRENA, which is another important website which gives the complete globally how much are we talking about, how much we are projection of the requirement, which is coming out in next 2-3 slides. So I actually worked in a national grid in UK when I was in TCS in UK for some time, where I was in IT department, but I know the entire business of how they do that, right? I was also part of an organization called Transco, which is today, as of now, it is called National Gas, right? So National Grid is the electricity transmission in UK, whereas the National Gas is transporting, the complete, transporting where it is getting produced. The gases are produced from the underground and taken, processed, and then it distributed to the entire city of multiple locations, right? So I was there for 1.5 years in UK, where National Grid and Transco was there in near Birmingham. So that is what I know their business very well. How do they charge the customer? So it's all rating, the pricing and all done based on the consumption. Peak hour rate is different, and winter season the rates are different. So many of those technologies are used. Optimum use of electricity was consumed. So, and when I was in TCS, in GE, I was servicing a customer called GE, where I was in technical department called computer system management, but my technical team was managing some of their GE production line manufacturing of those components, right? So I was part of that. So that's why I just wanted to touch upon that. I've taken some of the material from them in the following slides. Right. So Tata Power is an Indian organization where it is producing energy which is from the solar as well as the other wind power and all that. They have installed it. Power projects, another one. ABB Automation, I have taken some material from them. ILAB is another institute. I have taken it. Omicron, where I have taken some reference material on smart grid, and right. So the International Energy IEA, which is given certain documents, how much is being used, right? So we'll come to that. So India, there specifically says the growth of consumption of electricity is year on year, it is increasing by 8%. That's what the report it says. We'll go when you are coming to that slide, we'll talk about that. Right, that is what I'm going to talk about. So in the next 1.5 hours, I will be touching upon our agenda is in the following session. Right, I'll touch upon what is cyber physical system and how Industry 4.0 and how Industry 5.0. What are the difference? How do we transform ourselves in order to adopt and adapt Industry 5.0? Right. So Industry 5.0 has a specific technologies. Around 8 specific technologies are defined in that, right? Like big data analytics, one of them. AI is one of them, right? Blockchain is one of them. So we'll talk about various 8 of the key technologies where Industry 5.0 is defining, and we'll see how those technologies will be useful in terms of using our power engineering in power transmission or power generation or power consumption, any of those stages. So we'll touch upon that, and I will touch upon some of the points like how the Industry 5.0 can be applied in a smart grid. So, and later on, I'll definitely have to say one case study. The security of specifically the ICS, Industrial Control System security, is very critical for every nation, right? So, which is going to be supported by each of the nation interests, right? How do they protect like the thermal power plant or power transmission line and all that. If an attacker is able to get into that site, and it is going to produce a huge damage to the entire nation for a long period of outage will happen, right? So we'll see some of the outages which has happened in the past, right? And go in details about one cases in Ukraine, how the power outage was happened, and what were the how the attacker were able to get into the network and lived there for a long time before they take over the SCADA system, right? So we'll take one or two case studies and then go in much detail into that. So that is our agenda, right? So I hope it is clear. Any questions as of now, or everything is okay? My speed is okay, or anything anyone want to change? Okay, I hope it is okay. Thank you, sir. Thank you. Right. So let me go back to our fundamentals, like how the industry, the industrial version 1, right? 1780s and all that, starting with water and steam power was introduced, and then railroads were established, and it was mechanization was the fundamental for industrial revolution, right? In 1870s, electrification were transported from where it is getting produced and where it is getting consumed. Mass production was the major factor. An assembly line in the factory and all that, lathes were there, or drilling machine, or all the machineries were producing mass production. That was in the industrial revolution, where the components were produced, assembled, and the final products were given to the end customer. When it comes to the third industrial revolution, automation was the key, right? And computers were introduced in 1970s and all that, where when I was doing my master's in computer science in PhD Tech, around that was in 1983 or 85, correct? That during that time we were seeing computers and all that. In the olden days, the computers were Apple Mac was very old system. Apple computer was introduced at that time. All our Pragati computers, all our HCL was there, and many of those big timers were during at that time. Shiva computers were there, PC computers, Pragati computers were there. Those are the olden days, and where the my MS DOS was not there. Microsoft operating system was in a different form, right? So that was the stage in which we were starting our career and that by that time. So after education and all that, mainly on that year 2000, sudden boom came, right? The customer of entire world, right? Because of the year was introduced, was represented in all the computer program, two character, right? YY, right? Like we have the DD, MM, YY, right? So nowadays it is converted. After 2000, it was converted into DD, MMM, YYYY, four digit, right? So when the 2-digit was there in year 2000, Y2K problem came. All these scientists were describing that problem will how the after 1999, right? So computer will change to 00, right? The year will be represented. The year 2000 will be represented as 00. Computer may not function. That was the whole FER was created across the end business, right? So huge project where TCS and most of the other companies like Wipro or Infosys were taking projects to convert, simple conversion of a 2-digit representation of a year into a 4-digit. That was the major change during that time. After completion of that, it is a huge boom in computer. They were able to confidently offshore many of those software development activities to India. During that time, that is all happened during the third industrial revolution. 1970 to around 2001 or 2. And after that, it is a completely everywhere we were doing the digitalization. Internet was boomed up. Like now today we are using browsing and all that. That is called surface web, right? So which is the only 4% of that. Today in today's world, the 96% of the traffic in the internet is all in deep web and dark web. Getting into that is a huge no, you'll see how much of data is getting transmitted and all that. People were no, all the hackers were no, all the material which they were collecting in the web, which is getting sold in the deep web and dark web. The attackers were using script writing and all that, which is happening in the underground world, right? So all kind of Bitcoin kind of currency where the transaction, the de facto currency in when you want to do a trading inside the deep web and dark web, that is what. So that's what is happening around in internet. But today, if you see internet, so it has a limitation, right? So there is a number of it is represented in a form called address, right? Each individual devices are addressed in a form of a IP address, Internet Protocol IP address, which is a 32-bit address, right? So which has a by itself, by defining a 32-bit, it has its own limitation of number of representation of how many unique IP addresses will be there in the world, right? So since suddenly it is becoming every IoT devices also needs an IP address, right? IoT is Internet of Things, which every unit, whatever you have in your watch, which you are wearing on your hand, which needs an IP address, right? So if you go over the street, you will see many of those cameras which are collecting the live video stream, that is collecting and then immediately transferring to the wherever the data is getting collected in the cloud platform and all that. So that every unit also needs an IP address. Where will you go for an IP address for that? Because we have a limited 32-bit. So IPv6 was introduced, which is a 4 times of 32-bit. It's around 128-bit address. So with that introduction, the IoT we are able to sustain and creating we are able to millions and millions of IoT devices were getting installed, and then they are able to get the IP address. There is no shortage of IP addresses at all, right? And parallelly, artificial intelligence were also introduced. Today the de facto standard is everybody started using Chat GPT from Microsoft, right? There are other artificial intelligence tools are there, and until the Chat GPT was given to free of cost, like Google Chrome, where what we do on a daily basis, search engine, right? Which is people started adopting it and making use of the ChatGPT for creating PPTs, lecture classes, or assignments, and all that were used in on a daily basis for the school students and college students and all that. And other than that, it is having excellent doing research engineering with respect to ChatGPT, which is giving it is being a highly valued artificial intelligence tool. The artificial intelligence tools were there from around 2000 onward. But when people started adopting, people started using that tool, which is becoming a certainly high value, right? And nowadays, all other organizations like Google and all that waken up to come up with their own AI version of tool set, which is also having a neck-to-neck fight between ChatGPT and all. Some people are adopting to ChatGPT, some other adoption of other tools also going on, right? So when it comes to industrial revolution, right, the fifth industrial the industry 5.0 is focusing on personalization and cobots, right? Collaborative robots, right? Cognitive system. These are the three key aspects when it comes to industrial revolution, right? In industrial revolution 4, the mechanical devices or the electronic devices were taking the lead, and people, the manpower also just following it. They are not doing the governance aspect of it, right? So they are not governing it. It is the other way, like the industrial components were governing, we are following them, not as a leader for them. So which is the key problem within the industry 4.0, that is the reason they brought it up, the other version of industry 5.0, which they wanted to make sure the person, right, is always leading the all those other technologies. We'll see that, right? Right. So if you go into Industry 4.0, I'm just talking about two different components. One is on the technology pillar, and another one is on which type of industries, what they are using it, right? One is on the HMI, human machine interface, robots were there, control system, instrumentation, monitoring, sensor, were all there in the production line. Smart factory, right? What we call that smart factory, where it is being used to mass production, right? So which is used in multiple technology, like Industry 4.0 were used in cyber security, where your SOC center or SIEM or SOAR, all that, right? We use all that for detecting and prevention. And prevention is better than cure. So we computerize everything and then do multiple things in automation of the SOC centers and SIM centers in cybersecurity, right? Then we have the RFIDs, other Internet of Things. Boom has come. Millions and millions of Internet of Things, like you are even in a healthcare, right? You are people using many healthcare devices, wearable healthcare devices, which can monitor the body's status or with the BPs and all that. It is monitored and then directly communicating with the hospitals or the nursing home where the patients doctors are there, which is very useful. In attention will be given to a patient if there is a variation in BP or variation in other significant health issue, right? So which can be immediately a critical care. Patients also wear a belt kind of thing that is continuously monitoring the heartbeat and all that, which is continuously monitored by their doctors remotely, which is very useful. And then the patient's life is taken care by those doctors, right? Another aspect is on big data analytics, right? So the data are produced by various devices, various ways, in different forms, different the speed at which data is collected, the speed at which data are changing, it's huge. So the data collection, no single database is able to cope up with the processing those data, right? So we have to have some tool for big data analytics tool or different type of altogether. Your relational databases is not going to help, because the data are various forms and various varieties of data are collected, and the speed, right? Hello, somebody is asking some question or anything?
No, sir. No,
Hello?
sir. It was by mistake some participants have turned on.
Oh, not a problem. So, okay. So, yeah, big data analytics is one of the very key aspect of Industry 4.0, which is still another key aspect, which is continuing. So, out of Industry 4.0, which are the things that are continuing to be in Industry 5.0, apart from all those aspects are still valid. And in addition to all this technology, we have to have the human aspect, and other key aspect we will see that resilience and sustainability. These are the three additional triad which has to be added on top of Industry 4.0 technology. Then it makes the full Industry 5.0 aspect, right? So if you take the mobile technology, what do you think, right? What is the how many millions of mobile devices are there compared to your computer system? If you take, I just taken one example from one of the website, which is giving me the desktop versus the mobile across the world, right? So if you see from this report, it is showing the mobile devices are around 65% or 2.8 plus your tablet is 1.8. So approximately 65% of devices are mobile devices. Only desktops are only 35% of devices. Then we have to give more importance for how do we protect your mobile devices safely. The security attack can come through that, and we are using mobile devices for our power engineering as well. So we have to make use of protecting mobile devices in terms of when we are start adopting these technologies for 5.0. Okay, so where are we using Industry 4.0? Just before that, I just wanted to tell you about the RFID, right? Today we are traveling any toll gates, right? RFID devices. I mean, the sticker which is there in your vehicle automatically detect from your bank account, right? The toll fees, right? So which has been used by the queue is very short and people can quickly pass through the gate and all that, right? RFID is now becoming a part of our life. So all those technologies are part of our life, and which is not sufficient. That is what they are saying. Industry 4.0 is this technology itself is not sufficient. We need to add other key aspects, right? Let us come back to that. Why, why it is which is not sufficient. We'll come to that, right? So other 3D printing is used, and machine-to-machine learning, all that. Cloud computing is another key aspect, right? Everything is moved on cloud computing. By itself has IaaS.
கேட்டதுதான் இந்த சரவணன் கடையில இவங்க கூட ஆட்டோ ஓட்டுறாங்கல்ல அவங்க கடையில கேட்டோம்.
Yeah, please go on mute. Sure. Yeah. Infrastructure as a service, software as a service, platform as a service, those are all the things are default, which is the part of Industry 4.0. Let us go back to the next thing. Where are we using the Industry 4.0 application, right? So the number one is the Internet of People. Let we use the communicate with our group of people or relatives or the friends. Multiple groups are there using social media. Multiple social medias are there, starting from Facebook or whatever it is, Instagram or WhatsApp and all that. We do without that we cannot live on a daily basis, right? Smart homes are there automatically. It fills up your water heaters and all the many of those smart homes. Many of those devices what you have when you just walk in, lights are automatically switched on, right? Many of those electronic equipments are all controlled by your many of those devices, right? That is also done, right? Smart buildings are there, like all the controls are being controlled in through a console, or nowadays you can switch on your motor and all that, right, through on your mobile app. Many of those things have come in able to control through your touch of a button on your mobile phone. So many of those data are collected on the internet. The next thing is on the Internet of Things, right? So we talked about the smart mobility and all that. So smart grid is one of the components where we are going to see much more details. And the Internet of Services, right, where the smart logistics and all that. Today we cannot live without your UPI payment, right? So completely digitalized. Many of those for the business web, right? Complete business web is on digitalized, right? So we have many of those activities now. Everything, if you do even for a bank transaction, we have an app in that, right? We have an app in our mobile phone which is doing that. Any business activities, even you whatever so-called WhatsApp group, all now it's all transformed into a business as a business medium, business communication, right? Even if you want to book a gas, it's all based on WhatsApp. Olden days, we used to call a toll-free number. The toll-free number and all gone. Everything has come in a small one of your customer or call center through a WhatsApp. That is the reason is they are very easily reachable to the end customer, right? So the utility value of those small applications, even though we started using WhatsApp for saying good morning, but it has ended up in using everything our day-to-day life, even for gas booking or whatever your call your any of those, even for small everything, bank account, your insurance, every payment status, all things are part of your WhatsApp group. So that is how the business web has improved in Industry 4.0, right? So is it sufficient? That is what the question. Is it sufficient to just limit yourself with Industry 4.0, which is not the case. So Industry 4.0 has its own limitation. What is the limitation, right? It's unable to focus on the regenerative feature, which is what the entire world is looking for, right? So zero CO2, right? So which is we have to reproduce or regenerative, and we wanted to make use of a circular economy, which we will talk about in the circular economy is going to be in production, in manufacturing and all that, right? Where we reuse, recycle all those components, which is we should make use of that to protect our earth, right? Then another thing is the mandatory environmental dimension, right? That fossil fuel and efficient energy efficiency, natural-based solution, carbon sinks, restore biodiversity, new ways of thinking. Those are all the things which is there are limitations and started when we start adopting. I mean, we are already adopting Industry 4.0. Very few organizations who are not adopting Industry 4.0, they are going out of business. In olden days, right? They have something called Kodak camera and all that, right? So we used to take photographs using a film, right? Film has to be produced. The film has to be processed overnight. We have to go and give it to a processing unit. Overnight, they will make the negative and they will ask you how many prints you need, and the next day morning it takes 24 hours for them to process and give you. Today it's all done, it's all gone, right? Those companies were not able to adopt to the revolving Industry 4.0. They are out of business today, right? Completely, your mobile phone is becoming everything, right? Your mobile phone is your camera, mobile phone is your wallet, mobile phone is your bank passbook. Everything is your mobile phone is voice, video, everything you can do it, anything, right? So one single mobile phone make everything on your hand, which is completely transformed. Your all those business are come to an end user or a end device processing, edge processing, they call that. Edge device processing, which is having all those application what you need for a daily life without even knowing this is transformed. We never see, it's not a one-day effort, right? Over a slowly getting adopted. People are getting adopted to that, and they didn't even know that they have been changed over a period of time. Just by from last 10 years, it is completely transformed, right? Today, nobody takes paisa and money per. No, nobody goes there for a coffee shop and all that. They pay around 20-30 rupees to pay a cup of coffee, all are UPI payment. So such a minimum, even 1 rupee also you can transfer money through UPI. So such a transformation has happened in banking transformation. So it's all used to adopt to that technology, and then people are using it. So, but there is a limitations like what we are talking about is environmental effect, social effect, climate effect, which is need to be improved upon. So why can't we think about the other aspect of that? So when they start introducing to the concept called Industry 5.0, they are talking about the three key aspect, which we call that triad, right? Industry 5.0 triad. One of the aspect is the human centric, right? You bring back the human. Don't depend completely on AI, right? So you have to have a touch and feel of the human power, right? The governance power, right? The right brain of that. So some indigeneity, vision, critical thinking. It's not go by just by logic, right? Your programming is all completely logic based, and you have a AI. It is self-learning and doing some component of that. But still, we need to have on top of that AI. You need to have the manpower who is having the excellent right brain thinking. So he has to be make use of his vision, and innovations has to be there. So you brought back your human centric into Industry 4.0. That is what transformation of Industry 4 to 5, right? One is the human centric, number one. So number two is resilient, right? Or you can say number two is sustainable. Let me finish out. Resilient. Resilient is robust, right? Robust. It should be if you have a hit on your system by an attacker, you should quickly come back, right, without having any damage done to the business. So it should be resilient. You take about any of those things. If there is a sudden blackout, okay, let me quickly get back, right, within a short period of time. So that is what resilient. It should be an agile. It can be applied to any of those. Software development, agile methodology is being adopted. So people were using olden days, right, software development life cycle, a waterfall model, completely transformed. People today we are started using an agile methodology or Scrum or DevSecOps, DevOps processes, right? That's what they are using it. So completely resilient. Even Europe is made from January 1st, right? There is a Resilient Act they are bringing in. DORA called, DORA and the Resilient Act, which is any of those systems, banking system and all that are supporting banking systems. All of them should have a resilient system. Your customer should not be impacted for committed beyond the committed availability time. So which means they make every service line should have fallback mechanism or it should be able to provide the service without customer getting impacted. So the resilient is another aspect which other countries have started. They brought in a rule or a law or a regulation, everything, whatever you call that. So those things have been put in place, right? Resilience is the key factor on Industry 5.0. Next one is sustainable. What do you mean by sustainable, right? It is the purpose of making use of make the earth safe, right? We have to use circular process, right? Reuse, recycle, right? Reuse, recycle, recycle the natural resources, reduce waste. It should reduce the impact on the environment, right? So UNICEF has 17 goals, right? Out of 17 goals, let us look at what is very important for your power engineering, right? We are not going to talk about all the other things like poverty, zero hunger, and all that. So let us specifically talk about affordable clean energy, which is what very, very important for our power engineering. Number one, right? Industry and innovation and infrastructure. Another aspect where how do we transport, right? How do we make sure our industry innovate the new way of generating wind power or solar power? How do we transform? How do we optimize that? How do we optimize the turbine with a high efficiency and all that, right? Another thing is how do we responsible for consumption, right? How do we consume our power generated in a reasonable manner, and how do you consume those in an effective manner, right? Another aspect, right? How do we contribute to the climate action? So if you look at these 4 key aspects of the goals of the sustainable Google development, our power engineering has to contribute in these type of 4 goals, right? So we have to say, so now the goal is now clear, right? Once the goal is here, then we have to set up your process and procedure and all that actions to be done. So we have to use the technology to adapt and adapt a set of processes what we are defining. Right? That is the Industry 5.0, which is the one of the key aspects, like the sustainable development. So with respect to sustainable development in a process engineering, how do we do that? So which just now we talked about the 4 key goals of recycling, our affordable energy, clean energy, and responsible to consumption, and how do we innovate and then come with an infrastructure. I'm not saying the other things are not going to use. Definitely their education, definitely it is to be there. Otherwise, how do people working in power engineering also need to be educated and all that, right? So all the other aspect has priority number 2 or number 3, right? This is our priority. Number 1, priority, whatever I marked up, 7, 9, 12, and 13 are the key factors where we have to focus on the sustainable adoption of Industry 5.0, right? So why do we need Industry 5.0? What is that it is going to give to the end customer or your consumer, right? It is definitely going to reduce the cost of consumption, cost of power generation, cost of the price per unit power, whatever they're paying the bill, right? That is going to be reduced. Overall efficiency will be improving it, right? So you have empowered the workers remaining, they are in control. Like instead of machines are in control, you are going to take up the driver's seat and then drive the entire control. Your right brain, which is going to be most useful in terms of controlling, taking decisions, governing aspect, all that is coming from empowering your the manpower, starting from operation level, tactical layer, governance layer, empowering every aspect of those people level, which is going to be people are going to be remain in control over the machines, right? So it is going to be definitely going to be the safety and well-being, right? So when I talk about the OT, the operational technology priority, right? When you talk about the security, meaning for IT, we talk about CIA, confidentiality, integrity, and availability. Whereas in OT system, we are prioritized instead of CIA, instead of confidentiality, integrity, availability, we have reprioritized and completely changed the OT's priority of security. What is that? So number one is the safety aspect. Safety is more important. If something goes wrong, make sure people are safe. No damage to the life of any person, no health injury or the life-threatening activities should not be done at all. So safety is first priority for them. Second aspect is the power availability, right? The availability aspect. When they say security, it is indirectly meaning the safety, availability, and integrity. See, other confidentiality is taken a low priority, which is out of the triad. Reason is there are not much personal information is stored in any of the OT system, right? So priority wise, the safety aspect and then the availability aspect and integrity aspect should be taken priority. So which is need to be improved, and the well-being of the people also need to be taken care, which is what Industry 5.0 is talking about. Then it is also talking about the competitive edge, right? How your competitor is going to give lower cost at higher efficiency at an affordable price at a value to the end customer, right? So it gives you a competitive advantage when you use any organization who have started using the latest technology. Definitely they have the competitive advantage, the latest technology which is going to help them to boost their customers confidence, and then new customers will keep joining into that particular brand or variety, right? So other thing is you need to adopt and train. So evaluation of the skills has to be constantly new skills have coming up, and then it has to be redevelopment of people with reskilling is very much required. So which is also continual improvement is the key process, right? So when you talk about CPS and product lifecycle management, lifecycle assessment has to be done. Then you have to make use of augmented reality, AI, and circular manufacturing is the key aspect when you start using the Industry 4. Transforming Industry 4.0 technology with added the key aspect which we talked about, right? Which we need to be adapting into our manufacturing line. Right. So just to put in a nutshell, like whatever we talked about, Industry 3.0 is computerization. Industry 4.0 is computerization plus digitization, right? Everything is digitalized, online, cloud, and all that. So Industry 5.0 is fine, computerized, digitized. Then you have to bring again the human aspect, humanization. So you bring back the human into the circle or into the cycle, whatever development life cycle or any of those life cycle, you bring a human touch into that, right? When we say Industry 5.0, it has its own triad called human centric. Make sure it is sustainable and it is resilient, right? Sustainability meaning you have to just think about the 17 goals of UNICEF, and out of which specifically for power engineering, we are more concentrated on more, our priorities are the 4 specific goals of power engineering, which is safe, clean energy, how do we optimize and all that. So sustainability is, when you say sustainability, the 4 key roles has to come to your mind. So human aspect, sustainability, and resilience, right? Bring back, make sure the resilient aspect of power engineering. No more blackout. Even if there is a blackout, okay, we should be restoring the power in a short while. So that is what the entire goal with respect to power engineering. How are we going to do that is what we are going to talk about. Right. So any questions as of now? Hello, any questions? Can you proceed? Yes. Okay, thank you. So as we just talked about, in Industry 5.0, cyber physical energy system, and we have to do a mass personalization, right? So one dress fits, fit for one unit is not going to fit for everybody, right? So in Industry 4.0, we go to a shop where we buy ready-made dresses, right? So everything is ready-made, right? There is nothing called, if you say size and all that, it may be a pant size and all that, maybe 36, 38, there is nothing called 39. After 38, it is just 40, 42, like that. Or if you go there, SML, right? The small, medium, large, SML and all that. So it is a different form, which there is, but naturally, if you see a person, each person has a completely different having form and size and all that, right? So if you are wearing a shirt called small, medium, large, it is for the sake of wearing, we are making use of that. It is not actually fitting our body, right? So, which means if there is if you are the answer to that question is, so the cost of personalization is too high. If you wanted to buy a material and go for stitching, which is going to cost you, right, more than 3 times than buying a ready-made shirt or pant, right? That is the case, right? So that is the reason we are adopting to the readily whatever market is selling, we are adopting. So which means industry is driving the human. There is nothing called personalization industry 4.0, right? We are just buying what is there. In case there is a process, in case there is a technology, in case there is a everything is available for personalizing at a price which is less than you go and buy a ready-made shop. And people will automatically come back to this one. So mass personalization is going to drive the adoption of industry 5.0, right? If the price, the value is what the customer is paying, right? If I pay price and I return, can I get a value? If the ready-made dress is cheaper than I pay for a tailoring and then material cost, which is more than that, so I'll never go and buy that process, right? If the price of material and then personalization is the overall cost, if it is less than ready-made material, I will definitely choose this option. How do you do that, right? That is what the question is, right? So you have to do some mass personalization. Like example, right? The 3D printing is one of the mass personalization. You given a component which you need to be produced, right? Completely do a scanning of that and produce it in no time, right? Laser cutting and all that. So it is a personalization. That is the prototype. So how do we transform that prototype into a mass production? Right? Once we do that, the cost of producing is cheaper than your ready-made shop. This is what I'm giving an example in a retail shop, which you have to see how do we apply the same thing in your power consumption, right? The factory consumption, right? How do they consume? They were operating a 3-shift operation. So some company may be operating in a 2-shift operation. Why do you pay a price? The billing charge use, different timing, various methods are there, right? Every electricity board is giving a different slab price and all that. So it can be customized for the adoption, right? If you use that technology, then people will start adopting to those technology, those concept, right? So mass personalization is what going to drive your industry 5.0 personalization. If you do that, then people will be at a value which is where the end customer should give a better value, and at a price what they pay, if it is better than what they pay in industry 4.0, they always compare that, right? So if it is better, they will start adopting. Only then the industrialization can transform itself to a 5.0. Just keeping all the triad and all that's fine, but what is the end customer is going to get? If the end customer is going to get benefit out of that, definitely sooner they will be start adapting to that. Right. So we just talked about this is one of the paper which is saying the industry 4.0 is the picture is the missing people. That is what the driving aspect is, the governance aspect, or you call that innovation, or the right brain thinking, artistic view, so many other aspects of human touch which is missing in the completely left brain thinking of logic driven, program driven, whatever the system will do, what you say, what you said already programmed, right? So completely they do it on their own, right? Which is where the cyber physical system has to be start adopting the missing people. Once you start adopting this one, automatically you will be transforming yourself to version 4 to 5. Right. So what are the key technologies? This is a very, very important slide, what we are going to talk about. How the industry 5.0 technologies, how to be adopted. In order to adopt industry 5.0, these technologies, apart from your triangle called humanization, plus resilience and sustainability. These technologies need to be applied. When let us take one of them, right? Big data analytics. When you start analyzing data, you have to apply the triad of Industry 5.0 as well, right? So artificial intelligence. This is similar to the 4.0. It is also it was there in Industry 4.0, but you have to add the component of the three triad of Industry 5.0, and you have to apply to that. Only then it will be make use of that. Robotics was there in 4.0. Now it is called cobotics, right? Which is collaborative robotics, which is it is giving that aspect. Then the digital twins, right? What you are talking about digital twin is completely a simulation can happen with a live system, right? Augmented reality can happen using digital twins, right? So blockchain, we can completely know who your end purchaser of your power consumption, right? Completely you can know what is the pricing quote was given. So you have a complete transparency will be there using the blockchain, or what you call that, right? A hyperledger kind of concept. So you have, it's all decentralized, and not one single system is going to have everything, right? So you are completely transforming into a distributed methodology, distributed decentralized management. Digital identities are there, right? Efficient approach is there, right? So another aspect of blockchain. Then we have to talk about Internet of Everything, right? Internet of electronics, Internet of things, all that. So which talks about Internet of Everything, like supply chain, reduction of cost, intelligent network, right? Asset and productivity, right? So edge computing, which is another dimension. Edge computing don't do any processing at the central unit, right? You only collect the data at the edge devices. Edge devices are going to send the data your your wireless or the network, whatever you have, right? So the processing is done at the central location, meaning you are putting a heavy load on the central unit, and everything you have to depend on the central unit. So if you start giving decentralized and make sure the end devices, so much of power is there in your mobile phone, right? So can you start process your data at your mobile devices or at the end devices where the data is being collected, right? So which means you are going to offload the work from the central processing unit to the decentralized method, and you need to only send the output from your devices to the central unit. So it is going to the number of bytes, whatever it is going to transfer, it is already reduced because it is already processed the data at the end devices. Only the output is going to send. You are not collecting the data and then raw dump data is not sent over the internet, over the communication channel, right? So edge computing becoming the norm of Industry 5.0, right? So when you're putting more computing in the edge devices, we also need to take care of, there is going to be a threat. Cyber security threat is going to be there because attackers can easily get into the edge devices much more easier than you're attacking your central server, right? So they can get into them, and then they can slowly get into your network. So good thing is about Industry 5.0 with edge computing. Definitely processing is done at the edge where the data is getting collected. The huge potential for data transfer is less, and then computing is decision is made already, right, by the edge devices. But there is a vulnerability also is there. We have to take care of the cyber security aspect of that, right? 6G is going to be the norm in future, which is processing is done at a lower latency, can transfer. Very much is useful for IoT devices, right? IoT devices need to communicate to the central unit, central processing unit, and all that. So where it is getting collected has to be processed. So 6G is going to be the new norm in future. So when you talk about these are the 8 technology we have to start adopting when you are transforming our power engineering from version 4 to 5. Right? Let us see what are the challenges between Industry 4 and 5. Right? Where the focus is on production. Industry 4 is focusing on production, right? So whereas Industry 5.0 is human-centric, right? Human work, automation enhanced automation, right, with human work, right? So hyper customization. That's what the customization. What we talked about is mass personalization, right? So you produce mass personalized product. Like, if you wanted to go there, simple, like, want to buy your spectacles, right? So you are getting your own spectacles, whatever design you want, whatever model, in the outer, exterior, inner. Many of those components can be designed by you based upon your virtual reality or augmented reality units, and then you are going to say, this is what I want, immediately getting produced in no matter using a 3D printing unit and given to you within a wait time of half an hour to 1 hour. If you are going to give a mass production with that type of devices, right, your people will start adopting that particular thing. So no matter time, if those devices are available, automatically, like what we transformed, right? With mobile is everything in our life, right? Without mobile, people cannot live today, right? So which will happen over a period of time, in another 5 to 6 years now. Industry 5.0 is being being the norm for day-to-day life, right? So the governance, strategy and governance is what missing from Industry 5.0. We are going to be controlling, and we are going to be the strategy. We are going to do the practical, operational, and governance aspect of it, right? So the high-tech products, which are not the focus, where the customer experience is most important in the Industry 5.0, right? Sustainability of environment, which is not at all there in Industry 4.0, which is the core principle. Make sure we save our earth, right? So low carbon and all that. So that is the core principle. Technology integration is part of the human machine integration, human machine collaboration, right? With, even though AIs are there, AI will be not left alone. You will be controlling. Manpower is going to be the final control. Final decision will be made by it is going to be, AI is going to be supplement or support your human decision, right? Human decisions are nothing but the risk-based decision. So the risk assessment is done by the AI tools and giving you the various scenarios, option A, option B, with reasonable risk mitigation plan and all that. So final decision is always going to be the manpower, right? So this is how do we mapping Industry 4.0 with 5, right? So let us start. How do we start adopting Industry 5.0 with respect to the smart grid, right? So if you see that, right, India is there somewhere here, this area, which is nothing but 8% of rise, 8% of rise in electricity consumption year on year, right? 2023 to 2024, year on year, they are saying 8% trillion whatever in terms of their unit they are talking about. So all we know is 8% is overall. They are talking about in terms of TWH. The report is available from International Energy Agency. So which we talked about, our report came from right, daily report from the Ministry of Grid Control India, which we talked about. Let us go back and then see how we are going to make use of that smart grid. Right? What is the definition of a smart grid? So two-way communication, two-way electricity transform. It is not communication; it is a physical. The electricity is going to be transformed from where it is getting produced or where it is getting consumed and all that. Right? Wind energy, solar energy, all that is directly feeding into the grid. Right? So it is going to be monitored. How do you monitor and all that? Smart grid is according to the International Energy Agency, IEA, which is defining what is a smart grid. The definition says smart grid is an electricity network that is used the digital technologies, sensors, software to better match the supply and demand electricity in a real time, minimizing the cost and maintaining the stability and reliability of the grid. A smart grid uses an advanced technology to monitor and transport and electricity, right? So we have to use smart grid is the de facto standard. We have to use it. For multiple layers are there, right? It takes minimum 1 second for if you have multiple layers, layer 1 to reach the top layer, it may take 6 seconds to see the variation, right? Where the controllers, where the monitoring devices are there, it takes that. So which is what not acceptable to today's world. So we have to have in terms of milliseconds. In terms of milliseconds, once the data are collected, it has to be within a millisecond or as soon as possible. It should be displayed or put it in the plasma screen, right? So resilient power grid. So how do we make sure of your grid is resilient, right? You have to have anticipation. How do you anticipate? What is the future forecast of the weather? Because we are start depending on wind energy, solar energy. So weather condition is anticipation. How do we absorb, right? How do we absorb the peak load? How do we make sure the grids are stable and they are able to produce required power based on the consumption, right? Adoption and recovery. In case of downtime, in case of a blackout, how quickly you can recover back. So which is the 4 characteristics of the grid, and what is that going to give, right? It is going to reduce your energy waste, which is directly, indirectly, or directly supporting our sustainability goal. So when you start using grid, which is going to use, which is going to the energy waste is reduced indirectly, which is we are supporting our goal called sustainability goal, right? Enhance your energy transition, right? Improve your transparency and promote energy conservation, right? Minimize the cost and the environmental impact. Maximize reliability, resilience, flexibility, and stability, right? This is what the smart grid. So how do we use that, right? So smart grid manipulation, smart grid simulation is required. We cannot just switch on, switch off your systems, or we have to have a simulate in case of a load shedding and all that. You need to have some technology. The one technology which is supporting Industry 5.0 is a digital twin, DT, right? Digital twin in the smart grid, which is completely going to transform into 5.0, right? So we talk about, for example, various the power plants, digital, completely VPP, right? Virtual power plant we talk about, right? Transitioning completely you do have a digital form of physical system, right? Completely digital form of a replica of your physical system, starting from your where it is produced, where it is consumed, where it is transformed, where it is transmitted, right? Transmission line, distribution place, how does it? So you have to have a dynamically creating a replica of the load shedding in your digital twin, and then you can simulate what is the scenario. Based on that, you can quickly take a decision. And you have a prediction called consumption prediction, weather prediction, production prediction, energy management is completely at done service level, right? At a system level, smart PVs are there, right? Building level, how does smart cities, smart buildings are there? How does the infrastructure, either it's a factory or a home or a town, or how does it is going to be? You can simulate each one with a particular all our computer-based system-driven simulation tools are available. You can quickly create your entire system for even for our complete, our national grid. We can have the what we have is a national grid. Very good. Yeah. Here, what we talked about, right? So our 5 regions are completely merged into a one national level. So we can have a simulate entire thing into a digital twin, right? So we can do that. We using there are multiple softwares are available. You can simulate for that. One of the there are multiple software there. We'll see 1 or 2 tools later, right? So one of the electrical grid twin we can talk about, you can completely, this is a physical component, this is a completely digital component, the digital twin layer. You need to have the layer, how does it, the digital softwares are mostly set it in cloud data center, right? On a you can have it on a cloud data center or sometimes on a regional data center, on a plant data center. The communication has to happen using that. So you have the hierarchy, right? Level 1, level 2, grid layer and all that. So you can have this completely electric digital twin. And sometimes, how did we actually transform ourselves from the, transition grid, TG, traditional grid, TG, over a period of time, microgrid came, and then virtual power plant came, and then smart grid came. Now it's all IoE, right? Which is Internet of Energy system, right? Completely IoE. We are using it. Digital twins are used in the electric grid. Now we have started using a DT for us to simulate various scenarios of that, right? So what is that going to use? How it is going to be useful for us? It's more efficient, more secure, more affordable, and interconnected devices are there. So over a period of time, we transformed from microgrid to smart grid, and from smart grid we transformed ourselves to VPP, right? Virtual power plant. Now we are all in the scenario called Internet of Energy. Okay, Internet of Energy is make sure systems can be manipulated or managed using a load demand, IoT enabled processing, cloud computing, edge computing, information existence, consumer producer relationship. Okay, everything is a transparent manner, right? You use a blockchain here, right? Power generation status, all are there in the dashboard point of a tip of a person. It is available, transparency is maintained. We are adopting the governance is the core aspect of Internet of Energy, right? So when we are supposed to have Internet of Energy is the future thing, and if other countries have started already adopting it, we also need to transform ourselves from India. Our grid has to be transformed into IoE, Internet of Energy based module, right? So there are research work is already going on. Today we are in, if you think we are in the smart grid, right? Over a period of time, we have to get into a micro grid and nano grid. Nanoscale communication has to happen, right? And we have to start using blockchain technologies, right? Over a period of time, you can start thinking of quantum computing for processing. So much of big data analysis need to be done, right? Millions and millions of informations are collected in every minute or every the process status of devices are collected. Huge volume of data are to be processed. We need a computer system, which is today's computer system may not be sufficient. Once the quantum computing is put into production, right, we will start using quantum computing for complex energy management, right? Security will be improved, faster computation. That's what the core goal is, right? Later on, we'll be achieving your entire electric digital twin grid. So once you achieve this, it may take some time. Today we are in 2024. Next year, next 10 years from now, we'll be achieving this particular status when we are able to talk in the same forum, right? So grid also has a lot of complexities, right? It is grid vulnerabilities are there. Grid vulnerabilities are nothing but when I say security, you can assume it is how do you protect the availability of the power system, right? How do we make sure systems are not down, right? Systems are able to whether it's a production or transmission line or distribution line, at various stages, it has to continue to provide its services to the end customer, right? So grid protection is what we talk about that. Grid integration, right? Various devices are there, various communication channels are there, which has to be managed. Network issues are there. Security is availability and the safety. That's what the security aspect of it, availability and safety and integrity. These are the three key component triad for our power engineering, right? Cyber attack can happen. Just wanted to talk about cyber attack. Few of the cyber attack which happened some time back. Let us see. In specifically on the power engineering attack, we would have seen a history of that, right? Iran, Stuxnet, right? Where the nuclear, the centrifuge got attacked by Israel, thumb drive was transported and the Stuxnet program was running, which is the speed, the motor rotational speed was going 0 to the peak speed, and finally it broke the spindle. Right, many of those devices are what we call the centrifuge broken during 2010. Right, and then HAVEX in 2013. There is a ICS target, another major. Black Energy, Ukraine power grid was down for a period of time, and we'll see one of the case studies. Ukraine keep getting attacked by Indestroyer, crash over, one of the crash over attacking group. That was the software they used it. In 2016, power blackout was happened in their headquarters or capital. More than 6 hours of downtime. Right, Trinton crisis, an attempt in the Middle East happened, and Indestroyer, the second version of Indestroyer 2, again a blackout has happened in 2022 in Ukraine. Right, it keeps happening in Ukraine multiple times. And Pipe Dream, it's another attack, blackout happened in ICS attack in the framework 2022. There's a Russia also getting was attacked, under attack, Foxnet, and this is another recent attack in 2024. A heating system got attacked, an apartment of 600 apartment in Forsti Group was another attack. So attacks keep happening. It is not end, because unless, even though you have all the systems trained to identify, attacker is having a one step ahead of all of us, and they are able to get into the system through some weakness what we have. That is called system vulnerabilities, right? So security is to make sure the vulnerabilities has to be identified, and it has to be protected very well. Right. So what do we do? Right? We are talking about resilience. Right. So till now we talked about the sustainability aspect of it, and then the human factorization of that, and then the resilience aspect of Industry 5.0 we didn't talk about. So let us talk about how do we bring resiliency into the grid. Right. So you have to have a self-healing grids, right? If there is a one blackout happen in one of the smart grid, right, one unit where the power generation or power consumption, there is a complete breakdown. So you need to have proper, like in a network, we have a network segmentation, right? Similarly, you need to have a proper segmentation of those smart grids. So each one has to take care of the self-healing of within their grid itself, within their localized zone itself, right? So which talks about that level 1 zone, level 2 zone, level 0 zone, then the cloud aspect of that, right? So there are multiple communication protocols are there. In IT network, we'd always talk about TCP, IP, and HTTP, HTTPS protocol, and many of those things, right? So whereas in ICS, right, there are other OPC, UA, right? There are multiple protocols are there where components which are generated by various engineering firm like Siemens, everyone, they have their own technology. So finally, those component needs to communicate with the other devices, right? Which needs to very, very, very important. So there are standards being formed, OPC protocol, right? And MQTT protocol, MMS, which is IEC 61850, Goose protocol, right? MMS is excellent, the microsecond, right? In terms of the speed at which it is having in terms of millisecond, right? Within 4 seconds or something like that. For high speed, high security, we use Goose protocol, which is same technology of MMS IEC 61850, but Goose protocol is going to be useful for SCADA system, for high communication, large scale data processing. When we need to have large scale data processing, we have to pick the only option is Goose protocol. So which has been used in digital twins for the multiple units, whatever we have it in communication protocol. Wherever you see communication, one of this protocol will be in use, where it depends on what the units are there, what the units are communicating, which are the sender, which is the receiver. Based on that, the protocol will be decided, right? if it is not going to be an IT, right? Information technology protocol, very simple. Here, no, all the IP addresses, your TCP/IP protocol, your standard protocol are there. So here, Modbus, many of those protocols need to be de facto. We have to. The IEC is trying to bring many of the standardization. OPC is also bringing in many of the standardization. So people are started able to communicate with one devices of one company, able to communicate with the devices which are completely manufactured by another company. So common communication protocol, which is very much required, which is the de facto standard for that, right? So like what we are grid 1, grid 2, grid 3, and communication channel, what we use it, user interface, machine learning, since the data, whatever you collect, it's a huge volume of data, big data analytics, meaning you have to give it to LLM, a large language model to learn that. So you need to have a AI and machine learning. And then once the machine learning is there, you can do the data analytics of that, like whatever I showed in the first slide, right? So where our data are collected, huge volume of data are produced on a daily basis. So we need our proper data analytics to do that activities, right? So the same thing, right? The integration of the industry with, how do we integrate with multiple grids, right? We definitely need our digital twin, number one, and the physical grid. That is what you need to combine. How do we interface with them, right? You need to have the controlling units, and you completely need to have the IT team. IT team is nothing but cloud computing. When I say cloud computing, backup is there, automatic recovery is there, data processing can be taken care, online analytics can be taken care, management of aspect is there. So cloud computing is one of the component, big data analytics are another. So when you look from the left-hand side, where the field data is there, right, where your devices are collecting, field data are collected through PLCs or end devices, where the data are collected or data are processed at the local devices. You have the sensors, actuators, physical devices, where it is getting collected, and then local data processing, edge device processing are done at that place, local and remote database, and finally you have the regional database, which is getting connected to your corporate cloud central database. So we have to integrate. If you look at various challenges will be there. Whenever you see any component, when a component connecting to another component, there will be an interaction, right? When there is an interaction, there will be a friction. Then which means there is a challenges. You have to take care of that. It may be a security challenges. It may be a communication protocol challenges. So you have to think holistically. How do we apply that? How do we standardize our smart grid? So standardization is very much required. Then automation, then mass personalization is required, and only then you will be able to adopt to version 5.0. Right. This is another aspect of that. Another thing called EPIC twin, which is an electric power digital twin. You can refer this particular DOI document. Given a link here for you to go further in details of that, which is talking about how the smart grid, right, critical infrastructure. It is part of the critical infrastructure. When I talk about critical infrastructure, I just definitely I should talk about our India's critical infrastructure organization called NCIIPC, right? NCIIPC is our National Critical Information Protection Center, which is power and energy sector, which talks about all the government sectors, which talks about your telecom sector, right, health sector, and transport sector, SPC sector, and all the banking sector. So our interest is power and energy sector. How does it is supporting us? Let us take few examples of how it is continuously giving information, right? So adversaries, let us look at that. So it is continuously giving the end users like power engineering. We can look at that. If you are using a Mitsubishi electric equipment, it is as on 28th November, it has given a high status, right? CVE, or high, which is having some vulnerabilities, right? Vulnerabilities are there. What is the solution to that? It is somebody have found that is a problem if you are using a Mitsubishi systems, and if you are having a VMware, if you are in a Hitachi energy equipment, they are having a RTU 500 scripting interface issues, vulnerable. These are the electric security updates are there. This is another device which is having a problem. So continuously they are updating Palo Alto Network, Red Hat, these are operating in the IT. So IT plus OT devices, engineering equipments, power engineering equipments, having vulnerables, right? So one of those systems are installed, right? If you compare the life cycle of devices like IT and OT, IT systems life cycle is, if you install a server, right, life cycle is maximum 3 to 4 years, right? If you have a laptop, maximum you use it for 3 years, and then if you have an extended warranty, you'll use it for another 1 year and use it. Whereas those equipments which are what we have installed in power plant, right? We have installed it for 40 years, 50 years. No downtime. We will have a proper maintenance downtime. We will take it for a regular periodic maintenance. But otherwise, the system will not shut down, right? So systems which are manufactured 5 years back, 20 years back, how do we get the update? So vulnerable means vulnerable. We know that is a vulnerability. We cannot shut down our production system, right? We have to take a downtime, meanings only we will get once in 6 months. So during that downtime, all those security patches also should be updated, right? So these vulnerabilities are known, right, as of now. But when you actually do the implementation of those patches will happen only at when you get the downtime, when you get this planned maintenance downtime, right? During this time, the attackers can attack the system, right? This is a 0-day attack, right? Systems are vulnerable, as on 28th November, right? But you are not able to bring your system, Mitsubishi Electric equipments down for the next 2 weeks, right? Your downtime is only during Christmas holidays, right? Meaning you have to wait for 1 month, right? Within this 1 month, if the attacker are able to get into your system and bring down your system, you are going to be completely blackout, right? This is called 0-day vulnerable. We know the vulnerabilities, but we are unable to do the patching on those systems because of our own constraint, or the patches are not available from the manufacturer itself. Then that is also called vulnerable, right? Vulnerable scenarios, which is what I want to talk about in security aspect of that. Right. So how do we do the self-healing of that? You need to segment your network, smart grid, into island 1, island 2, island 3, and then you need to have a proper black start unit or non-black start unit and phasor measurement unit and all that. So if one unit is down in one of the group, right, there are constraints you have. You have to refer IEEE 39 bus fulfilling all that. So there are multiple ways that you can segment. How do you segment your smart grid into island 1, island 2, island 3? So dynamically done, and as long as you have able to meet those constraints, like the self-dependent islands are nothing but there are set of rules are there. Like each island should include at least one BSU together with one or several NBUSU, right? So those are like 6 or 7 constraints are there. If you are able to meet that, you can segment that, right? In IT field, there is completely different. Like we segment. Okay, this is completely OT is different, IT is different. Within IT also, we'll segment our network. This is a customer network. This is internal network. This is the DMZ network. This is an internet-facing network. This is an internal network. This is a proxy. This is a firewall. This is many of those ways we segment our devices in IT. Similarly, wanted to do a self-healing, you need to properly do the smart grid also in a island, which is based upon certain set of constraint which is there, right? That's one thing, right? We can keep talking about a smart grid. How much time we have? Any idea?
Sir, 5
Hello?
more minutes. 5
Right.
more
So
minutes.
I hope you will be able to give the presentation material to the
Yes, sir, absolutely.
participant.
We'll be sharing, sir.
Right. So I'll touch upon the few of the aspect of your big data analytics. What we talk about, all I'm saying is Industry 5.0, 8 technologies should be adopted to 3 core or the triangle or a triad of Industry 5.0, right? The humanization plus reliability plus your sustainability, right? Out of 16 or 17 the sustainability of the United Nations, 4 are key aspects for power engineering. We have to adopt that. Only when we do that, we can transform ourselves to Industry 5.0. So I will leave it to all that. Let me quickly get into a specific topic on how does attackers happen in the past, right? IoT devices are there, multiple devices are there. So let a smart grid is specifically we'll talk about smart metering, smart management, and all that. So what are the various standards are there, right? So the Center for Information Security, which is the US nation's national critical, like what we have NCIA PC, which we just now talked about, the power and energy for us, which is giving all the vulnerability notices and all that. They have a standard which every organization need to adopt and adapt. These are the standards we have. Like in ICS, we have the standard called 62443, which is nothing but Purdue architectural model for segregating. How do you segregate? Network segmentation, OT segmentation, IT segmentation separate. You have the separate. So there are standards ISA 62443 specifically for ICS systems, right? And also we have other standards like 61400 specifically for wind turbine, right? 61850 is for specifically for how do you do the protocol communications for various components in telecommunication between those devices and all that. OPC, like open platform communication, which is going to talk about your IEC 61800, 61850, 61950, and your UAE 61400 for the turbine, wind turbine, and all that. So there are other devices like ISA 95 for engineering, right? When you talk about, we are interested in energy, right? So those are the standard open system. DU also talking various frameworks are there. So you have the standards for we'll be using all that. These are the other organizations which is supporting common communication protocol platform, right? So MITRE is one framework which is MIT, Massachusetts Institute of Technology, MIT, world #1 university in US. They are research engineering wing, right? That is called MITRE. They came out of the MIT, and there's a separate unit supported by US funded organization. They keep identifying what are various attacks happening in IT, mobile, and ICS. You have to definitely need to look at this particular website, get into more details about MITRE. What are the various ways attack can happen in industrial control system? Like attacker is a APT, right? Advanced persistent threat, starting from initial access till they achieve their thing. The final thing is they will shut down, right? The final impact is denial of service, loss of control, loss of safety, completely brought down, right? Shut down your blackout. That is what the impact in power engineering, right? Safety and availability is going to be the impact. So attacker can come through that. This metrics from MITRE having an excellent, they have the complete history of the entire history of attackers, which I just showed you, right? All attacks are displayed in this particular metrics. You can see the material, whatever I gave, which talks about that. And one of the case study I talked about Ukraine, how the Ukraine was attacked, right? This is a Siemens controller, right? Siemens, what is it called? Siemens spike protection relay was controlled by the attacker, right? The protecting relay was compromised, and the SCADA system was controlled by the attacker. They are tripping the system. So final outage has happened, and it was for a 6-hour outage on a winter season. People impacted is 225K people were impacted during 2016. So this is one of the attack from Russia, right? So how that attack has happened, starting from end user compromising, end user clicked some mail, clicked a link, and finally they were able to take the control of the SCADA system. On the particular day, they tripped the the relay was tripped. Finally, the protective relay was tripped. So that is how 6 hours of downtime was there. So that was actually mapped how the attack has happened from starting from initial attack to the impact. The flow of attackers, tools, techniques, and TTP. This is called TTP, tools, techniques, and procedure, right? So this is what it talks about. and attacker were able to get into, bring down the entire transmission power line shutdown for that period. So we have to be very careful. Security is very is part and parcel of Industry 4.0 and 5.0, which is going to be forever. So protective mechanism or preventive mechanism is better than cure. So our systems will be resilient even some attackers happen. As long as we have Industry 5.0, since we are adopting one of the core function called resilience, we should be able to bring back our system back. The blackout will be a very short period of time, right? We can quickly revert back to our system. So you have the self-healing systems and all that. So I will stop here and then look for any questions or feedback. Thank you for your time. Thank you all for your patience. Anybody can talk about what did you heard me or give some feedback? How was the session or any questions?
Participants, you can unmute and ask your queries.
You can type in the questions in the chat box also. Thank you, sir. Since there is no questions, I will request sir to give the concluding session and then we can wind up.
Yes, sir. Yes, sir. Thank you. Thank you so much for the session, sir. It's highly informative, and we could see the participants actively listening to your lecture. And now I call upon Sudarshana to give the vote of thanks.
Thank you, sir.
Thank you.
As we come to the conclusion of this enlightening session, I take this opportunity to extend our heartfelt gratitude to our distinguished guest, Mr. Mayavannan, for sharing his deep expertise and invaluable insights with us today. Your remarkable journey of 36 plus years, coupled with your mastery of certifications and your impactful contributions to global organizations, has truly inspired us. Your guidance on cybersecurity, risk management, and IT infrastructure has enriched our understanding and motivated us to explore new horizons in this dynamic field. I also thank all the organizers and participants for their enthusiasm and engagement, which contributed to the success of this event. Let us carry forward the knowledge and inspiration we have gained today. Thank you all.
Thank you, sir. Please share the PPT to the participants. Definitely, they can look those links, whatever I given. Very much useful information for them to take their career. Thank you, sir. Thank you all. Bye.
Thank you, participants. We will meet again tomorrow evening in the same link. So we will be posting the feedback for this session shortly. You can complete the feedback and can leave. Yeah, there's feedback has been posted. You can complete and you can sign off. Thank you. Good night all.
Thank you.